Okay, so let's start today's class. A few announcements. Please decide on the groups. Let me know, 3 undergrad, 1 grad, kind of like that. Decide on the groups, and also think about which paper you're going to choose. There is this environmental paper, lead, concentration in pipes, and drinking water. There is nitrogen in Titan's atmosphere, isotope studies, and there is this manganese oxidation paper on Mars that also relates to oxygen in the Martian atmosphere. So, yes.
Are you going to upload those research papers?
I can, yeah, I will. Yeah, I will do that. Yes. Canvas, right? Yeah. So I can do that, and you can look at those papers, decide which. But the first thing is like form the groups, and that would make it easier, I think. But whatever, just let me know, and please let me know the date if anyone has any problems on November 30th as the date for class presentations, because I have to invite the 2 people to the class that day. Okay, so November 30th is the tentative date. So once we decide that this is the date, then I can go ahead and call these 2 scientists to the class. Okay, so in the last class, we did the piston cases, and the most important case in my opinion was the compression led to increase in temperature. We also started the concept of atomic structure, what is electron, proton, neutron, how the nucleus is the stable part, it doesn't change, and that is why alchemy is not possible. Because for alchemy, if you need to change anything into anything, basically what you're trying to do is changing the atomic number, because atomic number is the thing that controls the identity of the molecule. So you have any element, it has an atomic number, it has a mass number. So the mass numbers are not that important for the identity. It is important, but it's not tied to the identity of the element. For example, hydrogen can have 3 mass numbers, but as long as the atomic numbers remains 1, we'll call it hydrogen. Okay, and those 3 would be the isotopes of hydrogen. So we also discussed that. The different isotopes, if you have different proton numbers, you become, if you have the same number of protons, but you have different number of what? Neutrons, you become an isotope. So basically you have the same atomic number, and the different mass number, you become an isotope. Okay, so we discussed that. The isotone, what was isotone? Same number of neutrons, so N. Isobars, same mass number, like K40, argon 40, isobars. Isoelectronic, same number of electrons. For example, we did the example of Na+, which had 10 electrons, F minus 10 electrons. Also, isoelectronic is not just a single element thing. It can be a multi-element. It can be polyatomic species can be there. For example, N2 gas has 14 electrons in it. So 7 coming from one nitrogen, the 7 coming from other. You can also have O2 2+ as isoelectronics, because so if you have O2 2+, then this, if you can make this, then this also has 14 electrons, because O2 has 8 + 8, 16, and you remove 2 electrons, that becomes 14. Okay, so this and nitrogen becomes isoelectronic. Cn- cyanide is also isoelectronic with nitrogen. Okay, now I think Hunter gave me the solution attendance sheet, and Hunter, you solved this atomic structure practice questions, right? So I solved it myself, and these are the answers. You can check it. and let me know if you have any doubts. Okay? I also encourage the others in the class to also do it. It's very simple. How much time did it take?
Well, judging by my notes, probably about an hour.
Yeah. Was it helpful, like revising some concepts? Yeah, that's what I.
This is Gen Chem.
Yeah.
Too, so.
Yeah. Did anyone else have the time to do it? Anyone else planning to do it? Please. Yeah. Just do it. This will help you to do some of the problems that are there on the problem set. So this, I will discuss it completely. I'll give you the answers and everything so that when you do the actual problem sets, that will help. I cannot give you the answers to the problem set, of course, but I can give you the answers to these. That will help you to do the problem set. So you see, practice here, make less mistakes in the actual problem set. So that's the idea. Okay, so we did that. And O2 plus N2 Cn minus, I think this is an example from that problem set. So we did that. Now I asked you to watch chapter 6 on YouTube. How many of you did not get the chance? I mean, you did not. Okay, so I'll quickly go through Bohr-Boris principle and Aufbau principle. This, and I would say I am not going to spend too much time on this because that's an elaborate video. More slowly, that is being explained there. Here, I'll just quickly go through the Bohr-Boris principles and the Aufbau so that we can do some of the examples in class, okay? Now, what was Bohr-Boris principle for the people who actually saw it? So these are the two principles that we use to write down the electronic configuration of any element, it can have anything, okay? And when I say element, you understand there's an atomic number associated with that. So for any element or any even cation, anion, whatever, then you can know the number of electrons, protons, and neutrons associated with that element just by knowing its atomic number and mass number. Okay, so what were the 2 or 3 important things that we need to remember for Bohr-Boris principle? For the people who saw the video or remember, this is the 2n square rule that we did in high school, probably. Come on, the people who said they saw the video, what was that principle? Tell me, because I forgot.
The maximum number of electrons for each shell
is?
So you have n equals, or for KLM shells, it's n equals 1, n equals 2, n equals 3.
Right, so KLM, these are the different shells. K has, this n is 1, is 2, is 3. This n will become a little bit more complicated, not complicated, but it will get confusing a little bit. So this n and the n we'll discuss in principal quantum number n are kind of related but different, okay? In here, the first shell, which is the K shell, has n equals 1. So that's the first shell, is the shell number. This n is the shell number. So K is the first shell, L is the second, M is the third. So what is the maximum number of electrons that can go in the first shell? 2. So number of electrons, max, it's 2. For L?
8.
8. Because 2 times 2 squared is 8. 2 times 3 squared is 18. And so on and so forth. Okay, so this was the first rule, which is really easy. What's the second? So the first, what's the second? Not Hunter, someone else. Go on. There is the thing about the maximum number of electrons allowed in the outermost shell. octet rule, ring a bell? So the second was the maximum number of electrons the outermost shell can house is 8, right? So the valence shell can have a max number of electrons as 8. This is the second. The valence means outermost. And what's the last one?
Penultimate shell.
Yes. The penultimate shell, or the last but one. So this is the second last. The penultimate shell can have a max number of electrons as 18. Justin, do you have doubt?
No, I'm guessing.
Okay. Do you want to? Okay. Yeah. So the thing is, it's all about number of electrons. So the maximum number of electrons in any shell is 2n squared. It's determined by 2n squared. Now, the outermost shell, although it might have, so if the outermost shell is M, although it can house 18 electrons, if it is the outermost shell, then by the second rule, it can only get 8. That's the thing. And the other is penultimate shell, which is if you have, say, 7 shells. So M, O. So what's the maximum number of electrons here? 2n squared? How much?
32.
Yeah. For this?
50.
Okay. So now, if there is a atom, really big atom with big atomic numbers, that needs all these different shells to accommodate the electrons. Now, if the outermost shell is O, then, or it has 5 shells, the outermost cannot take more than 8, although 2n squared shells it can go up to 50. But if it is the outermost, it cannot go beyond 8. And n cannot go beyond 18, although this would have gone to 32. So that's the thing. Okay? Now, let's try a simple example, and then let's try a bigger example. Okay? So in the, what do you want to try? Because I'm not going to write it, you are. What do you want to try?
Sodium.
Okay, let's do sodium 11, 1123. Try this, K, L, M, and let's try lead 82. Quickly do this and try this, but even I cannot do it. So try, you might. Okay, let's try it together here. So we want to accommodate, how many protons are here? 11. How many electrons?
11.
11. Neutrons? 12. So this is an electronic configuration, so we just want to know about the electrons, because in the nucleus already has 11 protons and 12 neutrons. Any doubt in that? Okay, atomic numbers, mass numbers, that takes care of that. Now we just have to understand where the electron goes. So we have 11 electrons to house. So we start with the first shell. how many can it take? How many maximum can it take? 2. So let's assign 2, and we are left with 11 more. The second, how many can it take? 8. So let's do 8. Right? So this could have taken 8. How many are left? 1. So this becomes the electronic configuration. It's simple. Okay, let's try this, lead. So if we go 2, 8, and we might need these, okay? How many should we put here?
18.
I think, because it's a really big number. So we are done with 28 already. We are going to 82. How many should we keep here?
32.
I think. So 28 plus 32 gives 60, right? We are still left with,
So then 18 and 4.
sorry? Let's try just with the first rule, okay? And then we'll see what these tell us, and then we'll adjust, okay? So this gets 32, so I think this is 60, and then we get 22. But here, the rules are getting violated.
That one should be 18, and then the next should be,
So this,
that's the,
yes, so this becomes 22. Now this cannot happen, so we go with 18 to make this penultimate and make this the outermost. So this becomes this. 2, 8, 18, 32, 18, 4. Okay? It's a little complicated, not too much, but yeah. But imagine when you go to 103, 120, something like that. That becomes really complicated. Now, this is easy, but not so elegant. Let's now go to the Aufbau principle, which is the SPDF, and see what it has to offer. And let's see if it's easier than that or not. Because we are not trying to make things complicated. Someone might think that going from this to an SPDF, all this nonsense, is going to make it complicated, but it's not. It's actually going to make things much simpler. So I'm removing this. Oh my God. It is depositing more than it's removing. Yesterday I was suggested by one of my co-teachers, colleagues in the department, that the videos also help you to focus more in class. Because if you're frantically trying to take notes, then you might miss something that I'm saying. So now these things are really simple, but there might come a time where it might become a little more, you might miss something. But try to focus on what we are discussing here, and because the videos are already there, so you can always take notes going back to them, okay? Now, for the SPDF thing, I'm not trying to tell you what's there in the videos originally, but for those people who have not had the chance, I'm like, please go and watch it. But for here, we have to assume that these are the different orbitals that are there, and these are like houses for the shells, houses for the electrons. For example, like the S is like one home. It's like one home with a one bedroom, one house with one room. Okay, S types of homes. P is a 3-bedroom apartment. D is a 5-bedroom. And F is a 7-bedroom. Each rooms can accommodate 2 guests or 2 electrons. So any, so it can be 1s. So this can accommodate maximum of 2, because each block can get 2 electrons. So how many max can be accommodated in an S type of apartment? 2. For P, 6. 10, 14. Any doubts here? For the people who are like going back in memory lane trying to figure this thing out. It's fine? It's easy? Okay, now the arrows, the direction in which, so imagine these as balloons, and the arrows are trying to pierce the balloons. You're trying to find out which balloon is getting pierced first. Once you determine that, that is the home you're trying to fill in. Okay? So, when you have, say, sodium, we'll do that. We have 11 electrons, right? So how do you start? So which is the first orbital that gets filled in? Which is the first balloon that gets burst? 1s. So you start with 1s. Okay? How many electrons can go to 1s? 2. So you write 1s2. Some people write it above, bottom, doesn't matter. 1s2. Now, what's the next that gets hit? 2s. So you write 2s, and this also gets 2 electrons. 2s. So it's still S type of apartment, but it's just number 2. Right? Next, which balloon gets hit? 2p. You see, when it's coming in, this will get hit first and then the 3s. So 2p gets hit first, and this can take 6 electrons, right? Because it has 6 electrons. So this, how many we have already taken care of? 4. So this can go till maximum of 6. So this takes 6 electrons. Then what remains is 3. So this is the electronic configuration for sodium. Right? Now, we can go from this configuration to this configuration really easy. Now this, anything that starts with 1 is basically K, the K shell. Anything that starts with a 2 is basically the second shell, which is the L, and same for 3 is the third. So basically it again becomes 2, 8, 1. Okay, so you can go from this to that. Sometimes this will become easier and more informative than this one. Okay? So let's try lead. I'll give you a minute to try lead. It's really simple. Just follow that thing and do this and check whether this is correct or not. Because I don't know if it's correct or not. These two should, you should be able to get this from this.